Very quickly, let's get into the components of this BF03S pump. We have the mechanical seal, and that makes sense, otherwise the water will come out of the pump. We have the casing, obviously must have a casing. The impeller and guide vane. This is the impeller, this is the guides. Essentially we went through all of that. Again, very simple. We have a drain plug here, necessary if you're in a temperate country. Well, not really too necessary if your place isn't going to freeze, but yes, it's very convenient. If the place is going to freeze, you just turn this out and the water comes out. So makes sense for temperate countries. 2-compartment motor, that's this. Again, we saw the motor, single phase, most likely induction, with the start capacitor here, possibly start run capacitor. So yeah, stainless steel shaft, again obvious, you must have something that's corrosion resistant, so obviously it's going to be stainless steel, one of the best materials to work with. And then we have the air volume control. This is a complicated system. This we have to really get into, and I'll get into this right after. So this whole system here, one complicated system and not the most reliable, which is why we don't see pumps like this today. There are no pumps that I know of that have been sold this kind of system. Definitely Goulds doesn't seem to be selling this anymore. Check valve, as this here. And our check valve, the reason for this check valve is when the motor and the pump is on, this on the impeller is playing, we get a negative suction here, a negative pressure, and discharge here, positive pressure, and that comes out. As soon as you turn off the pump, and inside this entire pump, you will get, inside this whole cavity here, you will get the positive pressure, right? The pressure that the pump builds. As soon as you turn it off, all that water will then travel back through here, come back through here, and go back out into your suction line. So you will basically have no pressure in your system. Once you put a check valve here, that won't happen. The pressure that builds inside of here will be stopped, so the water will not flow back out into the line. So that's the need, that's why that is there. Here we have the nozzle for the clean out plug, and that is this here. And this has a high probability of getting clogged, and in fact the one we opened was pretty much completely clogged up. So this is the easy way to clean this out. You open this here and you run that out, and that's necessary for your whole jet system to work properly. And then we have the prime and plug here, which is this. Again, you're supposed to open this and fill up to here water, get the impellers fully immersed. What I did was be a little bit lazy about this, and what I did is just fill the water in from here. So I would have gotten it to discharge level actually about here. It may have some air bubbles in there, but over time when a pump is running, it will tend to basically get rid of all the air through the discharge. So chances are likely this whole thing is flooded right now because this system is compromised on the repaired pump, and we'll get into this now. Let's have a look at the entire system, how it would normally operate. Generally speaking, this whole thing here is for pressurization of the water. Water itself does not compress, therefore small leak, and you would lose all your pressure in your system. So generally what is done is you have a bladder and an expansion tank. One side has air, the other side is connected to the pump. As the pump pumps, what it does is it pressurizes the water stretches the rubber bladder compresses the air, and when the pump comes off, there's compressed air and there's water to pressure. As the water starts to come out of the system, the compressed air pushes more and more water down until it reaches the lower limit, when the pressure switch kicks back on and the pump pressurizes the entire system again. So what that does is it means the pump does not come on all the time. The pump comes on intermittently, not as often. They have chosen to do a casting in an extremely odd shape, and what they've done is they've made a complicated system to keep a certain amount of air. If you do this exact thing without putting this complicated system, you would initially get air up at this point. And what they've done is they put a deflector plate so that the pressure of the water has to come down and come. Eventually, after a period of time, when a pump is operating, there's a high enough probability that it will suck out that air. That air will eventually get pulled in at some point in time with disturbances and get exited through the discharge, in which case this entire thing becomes flooded. And when this entire thing becomes flooded, you no longer have an air bubble, a gap to cause the pressurization, so the entire thing will fail. There's no easy way to basically take that water out, no automatic way easily done, right? As I said from the beginning, that's why they do a rubber bladder. What Goulds have done here is a very interesting system. It's very well designed, I'll give it that. Not a hardy design, but an interesting design. What they do is essentially, because this is a jet pump, you have pressured water coming out from here and going into the discharge, but it's also going through this jet here. Because of this jet, you have what you call a Venturi effect, and you end up with a negative pressure at this point. So you end up with suction. That suction, right, will open this Schrader valve. This valve is pointing that way. So under negative pressure, it opens. And basically, once it opens under negative pressure, it will open here, and it allows anything from here. It allows any fluid from here to flow into it. That said, there's nothing flowing in because there's another Schrader valve here, and that is closed at this point in time. As the pump pumps and essentially this thing fills up, this is your normal level, operating level, and your float valve is there, and everybody's happy. There's some air on top here, system is working. As the air is sucked out and discharged through the system, this float valve goes up at an angle like this and reaches, let's say, our threshold, this red here. When that happens, this system here is within right here. There's a pivot point, as a rubber with a pivot point. That other side of it will press down on the Schrader valve, and what it does is it opens the Schrader valve. Now remember, this valve is always open once this jet is working. If the jet isn't working, that isn't open. But the jet, let's assume, is working because it's supposed to be working, right? So as soon as that happens, we now have full connection between here and there. Here has a negative pressure, so it's pulling, and it just happens to be a small hole here. So air comes in, goes through this, comes through here, goes in, gets pulled in by the jet, gets shut through the whole impeller system, comes out here. Of course, it's air. It rises to the top, fills back up this chamber, and the float valve goes back down to here. As it goes to there, basically it's not pressing this anymore. This valve shuts off. This is a hole, so this is also open, but this shuts off. No more air can enter the system, and the system remains balanced. So that is the method they use. Problem at hand here is that you're relying on a pivot of a, but it's created by a piece of rubber through here, and that's sealed to work. This is zinc, and this is a complicated system. It in fact corroded out here, and that's why that didn't work. You're really working on a pivot and hoping that works to press one Schrader valve to open another Schrader valve. Life is a lot simpler when you just bolt a piece of blasted rubber right across here. Same effect, same thing, simpler solution. So that is why I think it's an interesting engineering design, but it's not used anymore because it's too complicated. There are simpler ways to do the same thing. Using the same illustration, I just a little zoomed in now. Let's have a look. This is the inlet, and I'm using red is because it's pretty easy to see on the drawing. So this is the inlet here. Water comes in, goes through the check valve, which we described already. It's coming in here, and it squeezes through this little space here, goes through the jet, and reaches the impeller at the center. It then comes in here, and because of centripetal force, it gets pushed out. It's guided through here, comes out, and this whole chamber gets pressurized. Again, this is the outlet here. So as it gets pressurized, water flows and flows through. But remember, we have a negative pressure here. We have a suction going on here because water is being moved this way, and as a result, you have, well, some fluid must fill this space. So there's a negative pressure here. So some of our outlet water gets fed back into the inlet. Seems counterintuitive, but we'll get into why that's being done. This basically means when I'm taking this water and I'm shooting it through here and I'm basically restricting and getting a small nozzle, what we end up with is a Venturi effect. Essentially speaking, the water must speed up and flow through here very fast. As it does that, it reduces the pressure at this point even further. So here has a very low pressure, and essentially it goes through here. Now the amount of recirculation, right, is fairly complicated. We're going to get into just a quick glimpse of some of the formulas after, but anyway, the amount of recirculation, we are putting energy into water and we are bringing it back around. So we're losing energy. We are going to be less efficient. Why does this make sense then? Well, it makes sense because what I'm doing is creating a higher negative pressure here than I would have had if I had this closed off. If this was just pulling from here, the negative pressure here would not be as high. So as a result of shooting some water back and that Venturi effect, I get a higher negative pressure, lower pressure zone here. Therefore, I can increase my lift. Straight centrifugal pump does not have the kind of lift that you would get from a jet pump. You'd get a couple feet from a normal centrifugal pump. With this jet, you will get into the manufacturer spec just now and see 25 feet. That's not going to happen with a straight centrifugal pump. So it's a compromise. What we're doing is we are recirculating water, losing energy to get a higher suction and be able to pull water from a greater depth. Now, that said, this is completely useless if you have a water source that is within a few feet below or further above where the suction line. It makes no sense if you have a positive inlet pressure to recirculate water, because you don't need this. It's inefficient, but it works really well for wells. Now, it's not good for the application, the person who I had the pump from, but again, we got stuff from the US. I mean, we're close to the US and everything comes from the US, and there are a lot of wells and remote places, they just drill wells. Apparently they get permission fairly easily to do that. So there's a lot of jet pumps. Hence the reason we get jet pumps here. Duly warned that it is going to get a little more complicated now, and if you have an aversion to the maths or the physics, now would be a good time to just end. This is the information of the manufacturer. Alright, suction, lift in feet and gallons. I've translated that here, same numbers here, and just really split that up and did it by converting and getting the exact values. So pretty much the same thing. Again, this isn't too important. So taking this and bringing this into metric, because no one really wants to work in imperial. It's just, I don't know why anybody would want to, but anyway. So converting this into metric, this is the meters equivalent of this. Again, GPM, forgetting GPH, this is liters per second equivalent. If we consider that 1 psi is 2.3 feet, which is 0.7 meters, 20 psi, which is what we're working with here, the 20 psi discharge, and the only one we're working with here, we're ignoring this side, what we will end up with is about 14 meters, again, discharge. So the energy from the suction side, energy to lift something, mgh, potential energy, essentially. That's what we're doing. We're putting potential energy into the fluid. So mgh, the mass is the same as the liters per second. 1 liter of water is 1 kg. So the mass is that 0.052 by the height by g. We'll end up with about 8 watts of power required. And at that particular discharge pressure of 20 psi, we have 14 meters. So instead of that, if we work our energy out with the same formula, we'll end up at 75.9. If we sum this, we get 84.2 watts. The manufacturer stated it's a half horsepower motor. And that sort of makes sense. I mean, they initially said it was going to do 1/3 horsepower, but now it does half horsepower, as you can see, half horsepower instead of 1/3. 1/3 is just really dodgy. So half horsepower motor. The efficiency, if we consider a half horsepower motor, 1 horsepower is 746, so we divide it by 2 and work out efficiency of 22.6. This is the total efficiency from motor, power coming into the motor, and power out on the water. This includes the efficiency of the motor itself and the pump. If we want to see what the pump itself does, what we need to do is assume what the electrical efficiency of the motor is, and I'm assuming 65, and we'll get a little further as to why I've chosen those numbers. But going with 65, if we work this back up, what you will find out is that the efficiency of the pump is around 34.7, and let's get into some further literature to show that that seems just about right, and this seems just about right. And these are the two things we're looking at: what's our efficiency and what's our assumed motor efficiency. Single phase induction motor, what's the efficiency? Getting into these jet pumps and injectors, and this is of that particular article of Thermopedia by Mr. Green, and really good article actually. Some of the stuff just skimming through quickly and getting into the relevant points for us. We have the N ratio, which is based upon the pressure 5 minus pressure 2, pressure here minus pressure here, over pressure 1 minus pressure 5, pressure here before the venturi, pressure here. So that's the first thing. The second thing is the flow ratio, volume 2 over volume 1, that's M, right? This N, when they sit down and they work this whole thing out, that nice looking thing, they ended up with this. So let's just pretend that makes sense somehow and move on. And what is interesting is this is the efficiency curve that they came up with, typical jet performance curves, and as we can see, it appears to be around 34-35% maximum efficiency at a ratio of 1, and that is pretty much what we've just calculated and what we've based upon our assumptions. So now all we need to do is verify the assumption that the motor efficiency is 65, and everything makes sense and matches back up with literature that we could find in the field. This is the information off of Baldor, which is a fairly good pump motor manufacturer, and this is for a half horsepower 3450 RPM 115-230, which is extremely similar to the motor we have. Again, very comparable with what you would get on the Goulds pump, and again we looked at that speed, and this is the nominal efficiency, 66%. So we are very close, saying 65%, 66%, give or take, same damn difference. So really it makes sense to use that efficiency, and as I said, 115-230 single phase motor. And the one last thing that we want to do is have a look at the efficiency of a typical Goulds pump, preferably centrifugal pump without a jet. And this is a good example, half horsepower, right, Goulds technology. And if we scroll down this curve, all we see is this is our half horsepower curve here. We see 50% efficiency to 55%, just a little higher. So yes, pumps can get up to 68. I have known pumps to be up to 81%. 70, 71 to 80 is good. Anyway, apparently with these half horsepower pumps, they're not really that efficient, but at least 50%. So what have we lost? We've lost about 15 or 16%, probably 17, give or take, by having that jet. We've gained the ability to pull water from greater depths. We have lost that much, and that is us taking the higher end of the curve when we were just doing 5 feet suction. If we were doing 25 feet suction, we have lost over 28%, somewhere thereabouts, if I remember off the top of my head. You could just check back the video and see. But we've lost a lot if we try to suck water from a pretty deep hole. We're losing a lot, but if you don't have a choice and you have to get water from a hole, you need a jet pump. If you don't have to get water from a hole, don't buy a blasted jet pump. You're killing yourself for the efficiency.